just a beginning comment on what I mean by completely factoring. Let's just look at an integer. A factorization of 24 is 4 times 6, 3 times 8, 2 times 12, right? But none of those are what we call complete factorizations, because not all the primes, all the primes aren't present in these guys right here. Or they are, but it's not a complete factorization. The complete factorization right here would be 2 times 2 times 2 times 3. Okay, that's what we mean by completely factoring. Now, a lot of people might prefer the terser 2 cubed times 3. Okay, but again, these up here are factorizations, just not complete. Now, our goal here is to completely factor this 4-term polynomial, where the greatest common factor is just 1, right? So you can factor out the greatest common factor, but you don't get anywhere. All right. So the greatest common factor is 1. So this looks, at first blush, when I looked at this, it looks impossible to factor. But there's something that kind of motivates us here. This identity, if you'll notice, this particular identity at least has these 3 terms present. Okay. And that gets you to thinking about what you could do to make it happen. And have you heard anybody say that mathematics sometimes is cleverly adding 0? Well, that's what we actually do right here. We just put minus x cubed plus x cubed right here. Now that's equal to 0, but it gives us an advantageous opportunity to factor this thing based on this identity. And I've shown most of the work here, folks. You can kind of see what I've done here, hopefully. All right. Tried to get everything highlighted sort of to make it happen. But you'll see that this identity is connected here because we get the 3 terms, x cubed plus x squared plus x plus 1. Okay, but then we get to this stage right here where we note that x cubed plus x squared plus x plus 1 is the greatest common factor. It's present in both of these terms, right? Now, there's, let's see here, what do we have? Something that I always like writing here, and is once you start competing, this is obvious to you, but it's easy to forget that there's a 1 in front of this 4-term polynomial, x cubed plus x squared plus x plus 1. And that's exactly the one that you see right here. This one that I'm underlining down here is the coefficient of that 4-term polynomial. Okay? So you see what we get right here is a factorization. Okay, we get a factorization. This part right here is just x cubed times x is x to the 4th and so on, right? Now, you're asking, well, is it completely factored? No, a lot of you probably recognize, and this is almost by inspection right here. This is fairly common. You can think of this as having a common binomial factor of x plus 1, or you can just note that the multiplication x squared plus 1 times x plus 1 gives us those 4 terms. And that's just applying the distributive property. Some people call it fooling, which is an abomination, you know. It's just the distributive property. You get all 3 of these terms. X squared times x gives you x cubed. You get x squared, and you get 1. You get everything you need when you expand this out. Okay. Now we still have to finish it off. We have x to the 4th minus x cubed plus 1, and that is a complete factorization. Okay, so let me just circle that as our answer. And to me, it almost looks like a minor miracle, because I can see many people, even at advanced algebra level, saying this doesn't factor over the rational numbers. Right? I mean, if you look at it, you go, what chance do you have? You might consider trying to group things together, like factoring x squared out of the first term. You would get x squared times x to the 5th plus 1. But then x to the 5th plus 1 doesn't. You get a factor of x plus 1, but then you get alternating terms, not the the plus x squared plus x plus 1 type of thing. You get alternating terms if you try that, right? So literally, this is like magic to me to know that this identity, and you see, the identity, all it has is these three terms. So I call it some motivation, but I wouldn't call it some sufficient motivation. I don't know of how many people would honestly discover this unless they had seen it. I saw it in a competition problem. I saw the idea because my first reaction would be, this is, you can't factor this over the integers or the rational numbers, right? But then once you see this identity, you realize there's a chance owing to this notion that we call factoring, called grouping. Okay. So anyway, I would call this advanced factoring. I would say that a high percentage of the high school students in the United States could not factor this. Just a regular kid that made an A in his high school algebra or even his college algebra, you could show it probably to a professor of mathematics in the U.S. who taught, say, at a community college or somewhere, and they might not know how to factor it because it's really kind of like a hidden resource that's hard to discover, in my opinion. Let me know what you think about that. But I think that many people, if they're being honest and they're not using AI or something on this, they would say this is irreducible over the integers or over the rational numbers. Okay, but in any event, you can verify that what I've written down here is a complete factorization. All right, thanks for viewing.